So this problem is giving us two parametric curves in 3 dimensions, and both of them have the property that at time 0, if you like to think of this t parameter as a time parameter, which I often do when I think about parametric curves, at time 0, both of these curves are at the point 1, 0, 0. So R2 of 0, because the cosine of 0 is 1 and the sine of 0 is 0, we get 1, 0, 0 for R2 of 0 and also for R3 of 0. So both of these curves sort of originate, if you like, at that base point, 1, 0, 0, when t is equal to 0. So if we draw some coordinate axes here, x, y, z, then at time 0, both of my curves are starting right here, 1, 0, 0. And then as t goes from 0 to 1, so that's thought of as the domain of each of these two curves. As t ranges from 0 to 1, R2 is going to do something. And when it does that something, and we come back to R2 of 1, so where are these curves going to be at time 1? Let's check on that too before we go any further. So we'd have here the cosine of 2 pi, which is the same as the cosine of 0, which is 1. The sine of 2 pi is the same as the sine of 0, 0, and the sine of 2 pi is there. Right, so 1, 0, 0 is not only where the curve R2 originates, it's also where it ends up as t ranges from 0 to 1. And actually the same is also true of R3 for the same reason, right? That at 4 pi, 2 pi, and indeed any even integer multiple of pi, the cosine and sine functions are always in the same spot that they were at the other multiples of 2 pi. So both of these curves are curves that originate from 1, 0, 0. They do something, and then they end up coming back to 1, 0, 0 at the end. That's what makes them loops, and it's also what makes 1, 0, 0 a valid choice of base point for those loops. So the real question is, what are they doing in between? So I want to come back to this idea about period. That as t ranges from 0 to 1, how many complete revolutions are we going to make? Let's forget about the z-coordinate for the moment and just think about cosine 2 pi t, sine of 2 pi t. How many times does that wind around the origin in the xy plane as t ranges from 0 to 1? So the argument of this function is going to range from 0 to 2 pi times 1. So as t ranges from 0 to 2 pi, as t ranges from 0 to 1, and so the argument of these trig functions ranges from 0 to 2 pi, if I'm just looking in the xy plane, my first curve, R2, is going to make one revolution about the origin of the xy plane. And you'll notice also that both of these curves satisfy for all values of t that the y-coordinate is equal to the z-coordinate. And so that also kind of tells us how these results are oriented inside of 3-dimensional space. They lie in the diagonal plane y equals z. So it becomes something that looks like a circle, but the circle is sort of tilted in a way that it always lives in the plane y equals z. So it kind of comes up this way, and then it comes back around and down and back in. So this might be R2. And I'm going to kind of sketch in here the diagonal plane y equals z that this thing lives in. Right? So there's the first curve, R2. But in the time that it takes R2 to make that one circuit around the origin of the xy plane, or equivalently that one circuit around the z-axis in 3 space, what's happening with R3? It's going to go twice around. Yeah, because its period is half, or its frequency is twice what the other curve is. But otherwise, it would seem that it's parameterizing exactly the same curve, right? Because y is equal to z, and so this curve still lies in the the y equals z diagonal plane for all values of t. And it also lies on the cylinder, x squared plus y squared equals 1. Right? Cosine squared of 4 pi t plus sine squared of 4 pi t is equal to 1 for all t. And so it's parameterizing the same circle. It's just doing it in a way that in the time that it takes R2 to go around once, R3 is going around twice. So R3 makes 2 circuits around the z-axis. R2 makes only 1, as t ranges from 0 to 1. So, of course, the question is, are these two curves, do we expect that these two curves are homotopy equivalent really in any space? So we haven't like deleted a point or deleted anything from 3 space. If we just think of them as based loops inside of 3 space, are they homotopy equivalent? And the way that I've gone about kind of asking that question is kind of really specifically offering up this nasty-looking parameterized family of parameterized curves. So t is the parameter of the curve, h is the parameter of the homotopy. And so as h ranges from 0 to 1, the question is, does this family of curves interpolate in a continuous fashion between the curve whose image is R2 and the curve whose image is R3? So how did I make this nasty-looking family of parameterized curves? Where is that coming from? Yeah, I got this proposed homotopy by just combining together the parameterizations R2 and R3, with R2 getting a coefficient of 1 minus h, and R3 getting a coefficient of h. Right. So by adding those two things together, I get this family of parameterized curves, R of t and h. And so when h is equal to 0, what do I end up with here in this parameterization? This part goes away. This part becomes 1.
It's just R2.
So I get just R2. So if we're keeping score, and we probably should, if we're keeping score, that means that for this function, r of t comma 0 is equal to R2 of t for all t. And when when h is equal to 1, what happens?
You just got R3.
Yes, this part is just R3. This part, 1 minus 1, goes away. So R of t comma 1 is R3. So it looks like a duck and it quacks like a duck at this point, right? This function does seem to interpolate between R2 and R3 in a way that a homotopy should. So what do we think? Are these two curves, in fact, homotopy equivalent? Or is there more to the story? One additional more to the story consideration might be about the base points of the whole family of these parameterized curves. So suppose that I look at one of my intermediate curves along the way, not h equals 0, which would be R2, not h equals 1, which would be R3, but something in the middle like h equals a half. Right? If we actually want to, so if I plug in a 1/2 for h, what I'm really doing is I'm really just averaging together R2 and R3. Right? This is going to be 1/2 of R2 plus 1/2 of R3 as a parameterized curve. And so that's going to be 1/2 of cosine 2 pi t plus cosine 4 pi t. Cosine 2 pi t plus cosine 4 pi t. And then sine of 2 pi t plus sine of 4 pi t. And then the z-coordinate is the same as the y-coordinate. In fact, that happens everywhere along this homotopy. Let's see. So as we try and continuously deform R2 into R3 using this homotopy, all of my intermediate curves are still going to lie inside of this y equals z plane. What's less clear is whether they still lie inside of that cylinder x squared plus y squared is equal to 1, right? The way that the initial curve does and the way the final curve does. If I take cosine of 2 pi t plus cosine of 4 pi t and I square that, and I add it to sine of 2 pi t plus sine of 4 pi t quantity squared, let's find out if we actually get 1. When we square and try to simplify all of this stuff out, we get some stuff that simplifies. So this pair of terms here is going to simplify to 1, and so is the pair of terms that's on its right over here. So this pair of terms is going to add together to give me 1. But then I also have this sine plus cosine. There's probably some trig identity we could hit this over the head with if we really felt motivated. But at the end of a Monday, at the end of the semester, and without really high stakes on the line, I think I'll take a pass on that one. So the point is that this is no longer going to lie inside of the cylinder that it used to lie in. Sine of 2 pi t, but that's okay. Sine of 4 pi t plus cosine 2 pi t cosine 4 pi t. But notice also that when t is equal to 0, the base point, if you like, of this interpolated curve is also still going to be at 1, 0, 0, right? Because this cosine and this cosine are each going to be equal to 1. Add them together, divide by 2, it's going to give us 1. These signs down here are all still going to be equal to 0. And that's true everywhere along this interpolating family of curves, right? All of them are based at 1, 0, 0. And it would appear that everything here is continuous, right? There's nothing I've written down in this formula up here that would ruin the continuity of either each of the interpolating curves or of the homotopy that bends one of them into the other. So the curves are continuous, and the deformation that joins them is continuous. All the base points remain at 1, 0, 0. So, in our last class, we were able to convince ourselves that when we were looking at the fundamental group of the punctured plane, so the xy plane minus a point at the origin. So we were able to convince ourselves in our last class that in the punctured plane, if I take one loop around the origin counterclockwise and then stop, versus taking 2 loops around the origin counterclockwise before I stop, that's what this concatenation was, right? We do one and then we do the other, and if those are both the same, then I'm really just winding around the origin twice. That in this example, we decided that those two things were different, right? Homotopically different. There was no way for us to continuously deform the once around curve into the twice around curve. So back then, we decided that those two things were distinct. So the question for us now is that still true for this three-dimensional example? Because here, I've got the same kind of comparison, right? My R2 goes once around, R3 goes twice around. Are they distinct, or are they in fact homotopic? And this thing that we wrote down would appear to give us some reason to believe that they might be homotopic. So why don't I ask this? Maybe this is a way that we can kind of convince ourselves that everything is going to be all right in this example. What would make this picture on the right side of the screen here, what would make it analogous to the punctured plane example that we talked about last class? What could I do to this three-dimensional view in order to make it like the punctured plane instead?
Straight down the x-axis?
We can look straight down, well, one of the axes. I think if I look down the x-axis, I'm going to see everything edge on, and it's going to look kind of like a tilted, because I'm going to see this tilted plane. But yeah, if I look down, if I were to make the direct analogy to last time, I'd want to look from a viewpoint that's going to show me each of these paths as just a circle. Right? So maybe I'll look down the z-axis, or look down kind of at an angle from this way. Right? That would at least take my three-dimensional picture down into a two-dimensional picture. And so that's going to get me from the free space down into a plane. What could play the role of a puncture in an example like that? If I wanted to puncture this free space in the same kind of way that we punctured the plane, what should I remove from it? So if we consider punctured free space for a minute, I'm going to ask the question, give me an example of a homotopically non-trivial loop in this. If we consider 1, 0, 0 as our base point, how can I draw a loop in this space which is not contractible, which is not able to just be continuously crumpled up until it all resides at the base point. Here, this loop can be contracted down to the base point. All we have to do is lift this circle, this loop, just lift it up and over the puncture, and we can just crumple it all back up into this base point. So maybe let's draw a few interpolating curves. So we'll kind of lift it up this way, and then eventually sort of bring it to the other side, and then make it smaller, and we can just squish it down to the base point. So there's no problem, because we can go up and around this puncture, because we have 3 dimensions to work with now. We can lift up, we can lift down. So this kind of puncture is not analogous to what we had in the punctured plane. If I wanted to get behavior that looked more like the punctured plane, what would I have to delete? What would I have to take away?
You have to delete the whole z-axis.
Let's delete the whole z-axis. That'll do it. Because then we really are mimicking the same picture that we had when we were doing the two-dimensional case, right? If I take the whole z-axis away, and I have this loop that we drew a moment ago, now is this thing homotopically trivial? Can I squish it down to the base point? No, because there's no amount of lifting up or down that I can do. If I've taken away the entire infinite z-axis, right, this thing is pretty good and well stuck around that deletion. Right? So R3 minus the z-axis, well, that's a different story. And in fact, from a topology standpoint, even though this is 3-dimensional somehow, and our punctured plane was 2-dimensional, they should somehow be homotopy equivalent, right? R2 minus the origin. Because all we've really done, if we just look down the z-axis at our picture here, we would see the plane minus the puncture. Right? All we've done is we've taken the punctured plane and just added a 3rd dimension to it. And so when we added the 3rd dimension in the z, we get extra space above the rest of the xy plane, but we also get extra puncture lying above and below the original puncture that we had. So that's kind of more the picture that we would need in 3 dimensions in order to make this an interesting topological question. So in particular, that would mean that if we did delete the z-axis, we would be in exactly the same position that we were in when we were talking about whether or not the once around circuit and the twice around circuit are homotopic in the punctured plane. And there we answered no. It's not possible to deform one circuit into a double circuit. Because somehow, in order to do so, we would have to cross through the puncture in our homotopy. And so that, I think, should be the last thing to check here. If we deleted the z-axis from 3 space, would this homotopy still work? And I think our intuition now is that it should fail to work if we delete the z-axis. So to figure that out, let's just find out if there is any point in this homotopy at which the curve now has to pass through the z-axis. And how do we know if a point is on the z-axis or not? Like, what's true in 3 dimensions if a point lies on the z-axis? X and y both have to be 0. Right. So is there a place on this parameterization, will x of t and y of t, I suppose I need to put an h in there too, will x of t and h and y of t and h ever be 0 at the same point? Right? Is there a value of h which labels which curve I have in my interpolation, and a value of t which tells me where on that curve it's happening, at which that interpolating curve crosses through the z-axis? And that feels like an algebra problem, or a trigonometry problem, I suppose, that we can try and address. So if I were to set each of those 2 coordinates equal to 0, or another way to do it, and I guess it wouldn't work. I was going to say we could multiply them together and set them equal to 0, but then one of them could be 0 and the other was not. So we would really need to know whether there's a place where these 2 are equal to one another, and not only that, are equal to 0. So in our maple simulation, we just saw that we can, in fact, use this homotopy to interpolate between these 2 curves. But when we do so, one of the curves ends up needing to pass through the origin at some point. And so what we concluded out of that exercise is that, well, let me ask you, so what's our conclusion? If we just consider these two curves as curves-based loops inside of all of 3 space, are they homotopic? Are they homotopy equivalent? They are. This homotopy explicitly demonstrates that. We can deform one of them into the other, and we sort of saw some of the intermediate steps in our Maple simulation of what that looks like. So under what circumstances might they not be homotopic to one another?
There's a function.
If we had, right, if we have
Removing
taken,
the axis.
if we remove, say, the entire z-axis as an example, right? If we remove the entire z-axis, then it's not going to be possible for us to do this, like this homotopy in particular is not going to be valid anymore, right? Because this homotopy in particular, one of its interpolating curves crosses through the origin. That doesn't mean that there might not be some other homotopy that we could use. Right? In particular, Sam, your point about just removing the origin, if I just remove the origin, this homotopy would still fail to be valid, right? Because we actually do specifically cross through the origin at t equals a half for this. But does that mean that these curves are not homotopic in 3 space minus the origin? Well, not necessarily. Maybe we could just lift up this homotopy a little bit, add a little bit of extra z juice into it or something, so that when this cross through x equals 0, y equals 0 happens, it happens at z equals a half or something, to sort of nudge it up and add some extra lift to it so that we can lift that additional loop over the missing puncture, right? So we decided, after all, I think, that if it's only the origin that we remove from 3 space, any loop that I could draw is going to be contractible. Because we can always lift it up and over the puncture or down and underneath the puncture and collapse it all down to a single point. And in a situation where everything is contractible, that means that everything is homotopic to every other thing, right? Because they're all homotopic to the contractible loop, which is just a constant loop at the origin. So if we just remove the origin, it's not enough. What if we remove the entire z-axis? Then once around the z-axis versus twice around the z-axis are not homotopy equivalent anymore. Because regardless of how we would try to deform one of those two things into the other, that homotopy, that deformation, would have to lead to an intermediate curve that crosses through that forbidden z-axis.